So it's a new way of thinking about things. The math, the transform is easy. It's the sum over all n, that looks familiar, of x of n times z to the minus n. And that's it. It has an inverse transform that you will never ever use. It involves complex integration over the complex plane around a circle. Interesting stuff for one lecture of a graduate school course. Practically, I've never seen it used. But when I was an undergraduate and I saw this, I thought, this is dumb. And I thought it was dumb because of this guy. Firstly, z is a complex number. And I thought that if the magnitude of z was greater than 1, this thing would clearly decay away to 0 really fast, and it wouldn't pick up anything interesting of x of n, except for the really small values of n. And on the other hand, if the absolute value of z was less than 1, it would blow up for big values of n, and it wouldn't be interesting because it would only be sensitive to large values of n, of whatever x was for big values of n. And it would probably blow up so you couldn't sum it anyway. And what I was missing in what I thought, what I said just now is correct, but what I missed as an undergraduate was that the brilliance is that z is complex. And because z is complex, firstly, if x of n is finite, everything I said goes out the window. It doesn't blow up, right, if x of n only is non-zero for a finite number of samples. And secondly, the reason why it's interesting is not because it heavily weights either the beginning of the sequence or the end of the sequence, but the brilliance is that if z is complex, it chases itself as it's raised to a power around a unit circle. And let's talk about that. So first, even before I talk about the details of math, I want to talk first about just getting an intuition for how you actually use it. The idea behind this is that you have an input signal, x of n. It's finite length. Maybe it could be infinite length if it decays away quickly. But the point is that you take its z transform. Then you've got a system. Maybe you know what it is from its impulse response or from its difference equation. Or maybe you know what its transfer function is. You take its z transform. You multiply the z transform of your input with your transfer function in the time domain. Then you take the inverse z transform. So it works just like that Laplace transform in the continuous time domain. There's a couple of differences, though. One is that we have to worry about when things, if the z transform exists. So remember that the idea is that the z is just a nasty variable that we've created out of the blue that lets us do these transforms so that we can multiply in the frequency domain rather than convolve in the time domain, which is much harder. And then when we multiply in the frequency domain, that's the only reason why we have these z's is to let us multiply. We take the inverse z transform, we get rid of the z, and then we're back in the time domain. So the question is, does the z transform exist for any value of z? And for this to exist, I think you can see that the absolute value of a has to be less than 1. If the absolute value of a might be complex, but if the absolute value is greater than 1, then this thing will grow to infinity for large n, and the sum is not finite. So that's something to keep in the back of your head. The next thing to keep in the back of your head is that z is complex and then generally non-intuitive, just like S was in continuous time. The z transform exists for more sequences than the DTFT does. So as an example of why that's true, let's take 2 to the n u of n. DTFT does not exist. If you try to compute it manually, using the formula for the DTFT, you can see that this blows up. It doesn't satisfy that first bullet point. And so because it blows up, the summation is infinity, which isn't very interesting. And so its DTFT is just infinity, which isn't very interesting. It doesn't help you. Now, compare that with the x of z. Same summation. In fact, it looks a little bit nicer, doesn't it? Because you don't have that e to the minus j omega stuff. But using algebra, you'll need to be able to do this. We know what this is, and we can simplify this to 2 over z raised to the nth power. And if you've forgotten why algebraically, it's because z to the negative 1 is the same thing as 1 over z. So we've just simplified this to this. And now you can see that as long as 2 over z is less than 1, the z transform exists. And you can do a little bit of algebra with that. You can take the magnitude of the top and bottom is less than 1. So you can multiply both sides by z. Of course, the magnitude of 2 is 2. So that just means that the transform exists as long as the magnitude of z is greater than 2. So as long as this is true, the z transform exists. And that already suggests that there's 2 things we need to find when we find the z transform. We need to find out what that z transform is. That's pretty easy. We just simply throw that into our 1 over 1 minus a equation. And then we also need to find for what values of z it exists. And that's different than the DTFT. We never said the DTFT only exists for certain values of omega. The DTFT of a signal of a system, say, might be 0 for certain values of omega, and that just means it won't pass those frequencies. Or it might blow up. It might even become infinite for certain values of omega, and that means that it would tend to amplify those signals without bound. But the DTFT as a whole still existed, and here the z transform as a whole exists as long as you're evaluating it for absolute values of z greater than 2. Let me actually finish finding the z transform for this. So I'm going to continue on our evaluation of that down here. You'll remember let me give a quick recall block over here. We want to find the sum from n equals 0 to infinity of a to the n. Just plug in our numbers. That gives us a to the 0, which is 1, plus a to the 1, which is a. Continue on like that. Now we want to get rid of all these things, so we will multiply y by a, and that's just multiplying this thing. If this is y, we're going to multiply this by a. So 1 times a is a, this is a squared, this is a cubed. And now we will subtract them. So we get y minus ay up here. And of course, when we subtract all these things, this a subtracts from that, this a squared subtracts from this, and the only thing we're left with is just 1. So that means our y times 1 minus a is equal to 1, and therefore y has to equal 1 minus a. And of course, this is only true if that absolute value of a starts off as less than 1. So now we can plug this into here. We can see that this is our value of a, and so it's going to be 1 minus, it's going to be 1 over 1 minus a, where a is this guy. It's 2 over z, or as it's more commonly written, 2 to the z minus 1. And that's true for absolute value of z greater than 2. So this is the whole z transform. This is actually the Z transform. And this is the region of convergence, often abbreviated ROC. In fact, people generally call it ROC. And I think it's clear from this that you could generalize this to say that a to the n, u of n, has a Z transform that's 1 over 1 minus a to the Z negative 1, valid for absolute value of Z greater than a. And so this suggests that now some poor schmuck could have created an entire table of these things. And here's our table.